we're going to talk about the force length curve. Specifically, we're going to talk about preload and afterload. And then we'll also talk about specific applications or uses of the force length curve. And that's just my abbreviation there. The way that I think of preload is what happens before any load is placed on the muscle. Okay. Or what you can think of it as before any contraction. So you can use whichever term is better for you or whatever memory aid is better for you. Afterload is what happens after the muscle starts moving the load. Okay? The specific definition of afterload is the force required to move load. So afterload is the force required to move the load. The way that we actually generate the force length curve is that we utilize a specific apparatus, where this is a rig upon which we measure force, okay? And we suspend a muscle, isolated skeletal muscle in between here, okay? And we can move this rig up and down, so we can change the length of the muscle and we lock it into position. So what we're doing is we're measuring force per different length. And these lengths are fixed or discrete lengths. So what we have is a graph that will look like this. Force, length. And for each specific length, we measure the preload. So at many different points of preload, it will be 0. So preload is proportional to length. It's not linear with length. And at a certain length of the muscle starts to actually resist that stretching. So here you're going to stretch the muscle and you measure the force. You're not stimulating the muscle at all, so this is called passive force. It's also called preload. And this is the curve that you get. And this is called the preload. It's also called passive force. What we also do is we can stimulate the muscle, shown here with this little lightning bolt. So we stimulate the muscle and measure the amount of force that it generates. And we can do this for different lengths of the muscle. So when we do that, we actually can measure the total isometric force. And this goes back to your isometric curves. And this is your total isometric force. This is the total force that the muscle can generate at a given length. This is the passive resistance to stretching that the muscle can generate at a given length. Anything in between these lines, okay, anything in between these lines here is a result of active force. Okay, so anything in between there is active force, and that is where the actin and myosin interact to generate force. Okay, and I'd mentioned about this active force before, where active force is equal to total isometric force minus preload or minus passive force. So all this region in between here is the active force. It's important to note that these lines actually indicate the limit to which the muscles can be stretched. So this total isometric force delineates the total range of movement of the muscle. So a muscle at this specific length will contract, 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 contract until it reaches this point, and that's the maximum force that it can generate for that length, and it doesn't move. Okay? So that is total isometric. So we've talked about preload. Now we're going to talk about afterload. So an afterload is the total force required to move a load. So what's inherent in this diagram is that the force is equivalent to load. So this is length, okay, and the force can be equal to the force to move a weight. So let's say we place the afterload right here, and I'll just label that afterload. The muscle will contract and contract and contract, generating force until the force equals that weight. What will happen is then the muscle will start to shorten and you will get movement. Okay? And the muscle will shorten and shorten and shorten until it hits this curve. When the muscle hits that curve, it no longer shortens. And then the muscle relaxes and it comes back this way. And then it comes back down to there. Graphically, we've discussed this. This is called an isotonic contraction. Force per time. The muscle will generate force, generate force, generate force. So it generates force, generates force, generates force until it reaches this afterload, or the force is equal to the load that it has to move. When that force equals this afterload, so let's just write in afterload. When that force equals that afterload, the force that the muscle generates remains constant, so it stays flat, and then it reaches here. The muscle cannot shorten or contract anymore, and then it goes back down, and then it relaxes. Okay, so this movement here occurs within the isotonic phase. This movement here occurs within these regions here. So this is called the isometric phase, and this is the isotonic phase. So here, just to go over it again, you have shortening of the muscle. So what you can clearly see here is that from here to here, the length is changing. Here, the length is changing. Here to here, the force is increasing, but there's no change in length. Now let me just add the second part of this little graph here. Okay, so this will be length versus time. Okay, so this is force versus time. This is length versus time. And what you will have here, you will have that. So within this period here, the isotonic phase, when the force is great enough to move that load, you'll get this portion here going up like that. It hits that maximum force that it can generate. Then the muscle starts to go back to its original length down here. So I'll just do that again. Within this isotonic phase, which occurs here, you get movement here and movement here. On this graph, it will be movement here, so movement that way until it generates the maximum force that it can generate, and then it comes back down. So that is isotonic contraction, And that's actually how you can actually look at this graph to see how afterload affects the muscle contraction. Let's say I put the afterload down here. Well, it's very easy. What you do is you just draw your line up here, draw your line across here, and that is the amount that the muscle will contract. Okay? So that is one application of seeing how afterload plays a role in this force length curve. There's another thing that is very, very important, okay, that you can use to infer from this graph. So within this force length curve, there's something that you can infer from this graph. And it's very important. What you can see is that as you increase the preload, the amount of active force required to move a load is less. So I will just clean the board and draw it more neatly. So for a given afterload, so the afterload, the force is the same. Okay, so for a given afterload, the force is the same, but I'm changing the length. We'll draw the lines up here and across here. Draw these lines up here and across here. What you'll notice here is that you have to generate a lot more force, okay? A lot more actin-myosin interaction to generate that force to move this load. When you come over here, the preload contributes some force, okay, required to move that afterload. So what we find here is that the force generated by myosin and actin interaction, or the amount of myosin-actin interaction, is less to move that load. So the preload actually helps or generates some force so that the muscle has to do a little bit less work just to move that load. That is an application on how preload can affect the amount of work done by the muscle. So the preload basically helps the muscle move that weight.